On the 12th of August, satellite imagery over the South Pacific picked up an ash plume rising from Ambae, a volcano in Vanuatu also known locally as Manaro Voui, reaching an estimated 16,000 feet, close to 5,000 meters, into the atmosphere. The Wellington Volcanic Ash Advisory Center kept issuing bulletins on that plume for days afterward, tracking it as it drifted, thinned, reformed, and drifted again, a pattern typical of a volcano that has been in a low-level, sustained eruptive phase for months rather than producing one single dramatic blast. Vanuatu's Geohazards Department had already raised the alert level for Ambae earlier this year, and the activity in mid-August was simply the latest pulse in that ongoing unrest. That is the real eruption behind this story. Now here is the real question worth asking honestly, without dressing it up. Does anything happening on the surface of the sun right now have anything to do with it? The short answer, and it is worth saying plainly before going anywhere else, is that there is no established physical mechanism by which a solar flare or a geomagnetic storm triggers a volcanic eruption, and no credible volcanological research. Body treats solar activity as a forecasting input for eruptions. That is not a dismissive answer. It is the honest one, and the rest of this explanation is going to walk through exactly why, using the real solar activity that has actually been happening this week, because pretending the sun has been quiet would be just as inaccurate as pretending it controls the crust. Start with what has genuinely been observed on the sun, because it is dramatic enough without embellishment. A sunspot region catalogued as active region 4513 has been unusually active through the back half of August. On the 20th, it produced 3 M-class flares within a 24-hour window, including an M8.1 at 11:42 UTC, the strongest of that batch, accompanied by a radio sweep suggesting a coronal mass ejection was thrown off the sun's surface. Because the region sat near the sun's eastern limb at the time, that particular ejection was aimed away from Earth, out into space rather than toward us. 5 days later, on the 25th, the same region fired 16 flares in a single day, 5 of them M-class, the strongest an M7 peaking at 10:02 UTC, strong enough to cause a moderate radio blackout over parts of Africa. The forecast issued by the United States government's Space Weather Prediction Center for the following weeks calls for continued low-level solar activity with a chance of further M-class flares, and even a slight chance of an X-class flare, the most powerful category, through the start of September. None of that is invented. It is exactly the kind of solar weather that gets tracked constantly by space agencies, because it has real, well-documented effects on our planet's technology. Strong flares and the coronal mass ejections that sometimes ride along with them can degrade high-frequency radio communication, disturb GPS accuracy, increase drag on satellites in low orbit, occasionally strain high-voltage power grids at high latitudes, and light up the night sky with aurora far south or north of where it normally appears. A geomagnetic storm at G1 or G2 level, the kind forecasters were expecting around the 27th and 28th of August, as a fast stream of solar wind escaping from a coronal hole reached Earth, is a genuinely useful thing to know about if you are a satellite operator, an airline dispatcher planning polar routes, or simply someone who wants a chance at seeing the northern lights from an unusual latitude. What none of that activity does, according to the physics as currently understood, is reach down through several kilometers of solid rock and change the pressure of a magma chamber. It helps to be specific about why, because the claim sounds superficially plausible if you don't examine the actual scales involved. A solar flare delivers a pulse of X-ray and ultraviolet radiation that is absorbed almost entirely in the uppermost layers of Earth's atmosphere, the ionosphere, tens to hundreds of kilometers above the ground. That absorption does change the ionosphere's electrical properties temporarily, and that in turn is exactly why radio signals that bounce off it can degrade during a strong flare. A geomagnetic storm, arriving later as charged particles from a coronal mass ejection interact with Earth's magnetic field, does induce weak electrical currents at the surface, which is the same effect that can strain long conductors like power lines and pipelines during a severe storm. Those induced currents are real, measurable, and occasionally disruptive to human infrastructure. But their magnitude, even during a large storm, is many orders smaller than the mechanical stresses already at work inside a volcanic system, where pressures are generated by the buoyancy of molten rock, the release of dissolved gas as magma rises, and the slow, continuous deformation of surrounding crust. A magma chamber, a few kilometers underground, is shielded by that much rock, and the electrical and radiative effects of a solar storm simply do not carry the kind of energy needed to alter pressure conditions at that depth in any measurable way. This is not a matter of scientific opinion up for debate. It is a matter of the numbers not coming close to matching. It is worth pausing on where this kind of claim tends to come from, because it usually isn't invented out of nothing. There is a genuine and interesting field of research into much smaller, statistically subtle relationships between astronomical cycles and seismic or volcanic timing. Earth tides, the same gravitational effect from the sun and moon that raises ocean tides, also flex the solid crust by a small amount twice a day. And a handful of careful studies have found a weak statistical tendency for some fault types to rupture very slightly more often at certain points. In the tidal cycle, when a fault is already loaded right at the edge of failure. Some volcanologists have looked for a similar marginal tidal influence on the timing of eruptions at systems that are already primed and ready to erupt regardless. But there is a vast difference between a documented, small statistical nudge on a system already at its breaking point, established through years of careful data analysis and peer review, and the claim that a solar flare or planetary alignment is meaningfully driving eruptions or earthquakes on a week-to-week basis. The first is real, cautious, heavily caveated science. The second borrows the vocabulary of the first, terms like ionosphere, geomagnetic, and coronal hole, and uses that vocabulary to make an unrelated and untested claim sound like it belongs to the same body of evidence. It does not. The same caution applies to claims involving planetary alignments. Mercury reaches what astronomers call superior conjunction periodically. When it passes behind the sun as seen from Earth, simply a routine consequence of the two planets' different orbital speeds around a shared star. There is no physical channel by which Mercury's position in its orbit, at a distance of many tens of millions of kilometers even at closest approach, could meaningfully influence solar flare activity, which is driven entirely by the internal dynamics of the sun's own magnetic field twisting and reconnecting near sunspot groups. Sunspot cycles and flare activity are tied to an 11-year solar cycle driven by processes deep inside the sun, not to where a small nearby planet happens to be. When a burst of flare activity happens to coincide with a planetary alignment, that is coincidence dressed up as correlation, and treating it as a forecasting tool has no support in solar physics. So why does this kind of framing spread anyway, and why does it often sound so confident when it does? Part of the answer is genuinely understandable. Watching real-time solar imagery is fascinating, and the data itself, sunspot numbers, X-ray flux curves, chronograph footage of material blasting off the sun, is visually striking and genuinely educational when explained accurately. The problem arises when real, well-sourced data about the sun gets stitched together with an unrelated and unproven causal story about earthquakes or eruptions, using the shared vocabulary of energy and charge and fields to make the connection feel physically grounded, even though no such physical pathway has been demonstrated. A full moon is often blamed anecdotally for stranger behavior in emergency rooms, a claim that has been tested repeatedly in actual hospital admissions data and has not held up as a real, reproducible effect. Once the studies control for other variables like weekends, weather, and simple confirmation. Bias, where a memorable chaotic night under a full moon gets remembered while an equally chaotic night under a new moon does not. The same pattern of memorable anecdote outrunning tested evidence shows up whenever big, dramatic natural events get attributed to celestial timing. Let's go back to Ambae itself and give the volcano its own attention, because it deserves a factual account without being used as a prop for something happening 93 million miles away. Ambae sits in the Penema province of Vanuatu, an island nation strung along a subduction zone in the South Pacific, where the Australian plate is being forced beneath the Pacific plate, generating exactly the kind of volcanic arc that produces frequent, often modest, eruptions across dozens of active vents throughout the archipelago. Vanuatu's volcano monitoring agency has documented persistent volcanic tremor at Ambae through this year, along with continuous degassing, elevated sulfur dioxide emissions, and lava effusion inside the summit caldera that has physically altered the crater over recent months, filling in what used to be a crater lake with new volcanic material. This is a volcano behaving the way volcanologists expect an actively degassing, moderately restless system to behave, not building toward a single catastrophic event on any knowable date, but sustaining a long, grinding phase of minor eruptive activity that periodically sends ash a few thousand meters up. Enough to matter for aviation routing through the region, but not on the evidence available, signaling an imminent large-scale explosive event. Ambae is not the only volcano that has been active this particular week, and it is worth naming a few others, simply to show how routine simultaneous volcanic activity actually is on a planet with more than 1,000 potentially active volcanoes. During the same window in late August, ash advisories were also issued for Canlaon in the central Philippines, where eruptive pulses sent ash to varying heights on separate days, and for Ibu, in the Halmahera region of Indonesia, another persistently active vent producing regular explosive bursts. None of these are connected to each other by any shared triggering mechanism beyond the simple fact that Earth has dozens of volcanoes in an active eruptive state at any given time, scattered across multiple entirely separate tectonic settings on opposite sides of the planet. Multiple volcanoes erupting in the same week is not a sign of a coordinated global event. It is Tuesday, geologically speaking. If solar activity does not drive eruptions, what does explain a system like Ambae ramping up or calming down over months and years? The honest answer is a combination of factors internal to the volcano and its immediate geological surroundings. Magma supply from depth can increase or decrease based on processes happening in the mantle far below, changing how much fresh material is feeding into the shallow system. Gas content in the rising magma plays an enormous role because dissolved volcanic gases, mostly water vapor, carbon dioxide, and sulfur compounds, come out of solution as magma rises and pressure drops, similar to bubbles forming when a bottle of carbonated water is opened. And the rate at which that gas escapes determines whether an eruption is a slow, effusive process or a violent, explosive one. Local groundwater interacting with rising magma can trigger phreatic explosions, sudden steam, blasts, when water flashes to vapor on contact with hot rock. Structural changes within the volcanic edifice itself, cracks opening or sealing, the summit crater's shape shifting as material accumulates, also change how easily gas and magma can reach the surface. All of these are measurable, physical, local processes that volcanologists monitor directly with seismometers, listening for the tremor caused by fluid movement underground, tilt meters, and GPS stations, detecting the ground itself swelling or subsiding as magma accumulates or drains, and gas sensors measuring sulfur dioxide output as a proxy for how much fresh magma is degassing near the surface. This is the actual toolkit used to assess volcanic hazard, and it is a toolkit built entirely around instruments placed on or near the volcano, not instruments pointed at the sun. That contrast is worth sitting with for a moment, because it gets to the heart of why the space weather framing, however entertaining, ultimately misleads more than it informs. A volcanologist, trying to assess whether Ambae's activity is likely to escalate, looks at the deformation data from GPS stations around the summit, at the trend in sulfur dioxide output over the preceding weeks, at the character of the seismic tremor, whether it is shallow or deep, continuous or episodic, and at the historical eruptive pattern of that specific volcano going back through its documented record. None of those inputs come from the sun. The instruments that actually matter here are buried in the ground or orbiting close enough to look straight down at the crater, not instruments watching a sunspot group 93 million miles away. It is also worth being fair to the genuine uncertainty that does exist in eruption forecasting, because that uncertainty is real and shouldn't be papered over in the other direction either. Volcanology remains, in an honest sense, a probabilistic science rather than a predictive one. Monitoring agencies can identify when a volcano's behavior has shifted into a more concerning pattern, rising ground deformation, escalating seismicity, changing gas chemistry, and can raise alert levels accordingly, the way Vanuatu's Geohazards Department did earlier this year for Ambae. What they generally cannot do for Ambae, or for almost any volcano on Earth, is name a specific date on which a larger eruption will or will not occur. That genuine humbling uncertainty is precisely the gap that speculative causal stories tend to rush in to fill, because a confident-sounding narrative involving solar flares and planetary alignments feels more satisfying than an honest shrug backed by real but incomplete data. The instinct to want a clean explanation is understandable. It just isn't the same thing as having one. It is worth spending a little more time on how the actual monitoring pipeline for a volcano like Ambae works day to day, because it illustrates just how far removed the real hazard assessment process is from anything happening on the sun. A network of seismometers, positioned around the volcanic edifice, listens continuously for the distinct signature of volcanic tremor, a sustained, often low-frequency rumble caused by fluid, whether magma or hydrothermal water, moving through cracks and conduits underground, which reads very differently on a seismograph than the sharp, brief signal of a tectonic earthquake. Continuous GPS stations track the ground's position to within a few millimeters, watching for the slow inflation that indicates magma accumulating in a shallow reservoir, or the deflation that follows an eruption as that reservoir empties. Gas-sensing instruments, sometimes mounted on the ground and increasingly carried by drones for closer, safer sampling, measure the ratio and volume of sulfur dioxide and carbon dioxide escaping from the summit, because a rising ratio of these gases relative to water vapor often signals that fresh, gas-rich magma is approaching the surface rather than older, already degassed material simply recirculating. Satellite thermal. Imagery adds another layer, picking up hotspots at the crater or along flow paths that aren't always visible from the ground, especially useful for a volcano on a remote island where staffing a permanent ground station near the active vent isn't always practical. All of this data gets synthesized by the National Geohazards Agency, in this case, Vanuatu's Meteorology and Geohazards Department, into an alert level that communities and aviation authorities can act on. It is a slow, careful, instrument-heavy process built entirely around watching the volcano itself from as many angles as possible, and it has absolutely no input channel for solar flare data, because there is no established reason one would be needed. It also helps to understand why claims linking space weather to geological hazards tend to persist even after being examined and found wanting, because the reason is more about how evidence gets evaluated than about any new discovery. A single dramatic coincidence, a solar storm arriving the same week as an earthquake or an eruption, is vivid and memorable in a way that a null result never is. Nobody makes a video about the many far more numerous weeks when a strong solar flare occurred and absolutely nothing unusual happened anywhere on the ground, because there is no story there. That selective attention, remembering the hits and forgetting the misses, is one of the best documented patterns in how people evaluate unlikely claims. And it applies just as strongly to natural disasters as it does to any other domain where someone is looking for a hidden pattern in essentially random timing. Rigorous science tries to correct for this by looking at the full record rather than the memorable outliers, comparing how often eruptions or earthquakes happen during elevated solar activity versus during quiet solar periods across many years of data, and when that comparison has actually been done for volcanic eruptions specifically, no statistically significant relationship has emerged that would justify treating solar activity as a forecasting tool. There is one more distinction worth making clearly, because it separates legitimate scientific caution from the kind of narrative that borrows scientific language without scientific rigor. A real geophysicist studying a possible small tidal influence on seismicity will publish the effect size, however tiny, alongside its statistical uncertainty, will note which fault types and tectonic settings the effect was and was not observed in, and will explicitly caution against overinterpreting a marginal statistical nudge as a predictive tool. That kind of claim comes wrapped in hedges, confidence intervals, and peer review, precisely because the researchers making it understand how easy it is to see patterns that aren't really there in noisy geological data. A claim that a specific planetary alignment or a specific flare sequence explains this week's volcanic activity, offered with total confidence and no statistical framework behind it, is a different kind of claim entirely. One that sounds similar on the surface, but has skipped every step that would normally separate a tested hypothesis from an appealing guess. Confirmation runs backward. When a big flare happens, and nothing notable follows on the ground, that pairing is rarely mentioned. Again. When a big flare happens to fall in the same week as a volcano that was already erupting for its own well-documented reasons, or a modest earthquake in a region that produces modest earthquakes constantly, that pairing gets remembered, repeated, and treated as evidence, even though volcanoes are erupting somewhere on Earth essentially every week, and the sun produces flares on a regular cadence tied to its own 11-year cycle, which happens to be approaching a period of peak activity right now regardless of what any planet is doing. Two frequent independent phenomena will inevitably overlap in time on a regular basis purely by chance, and noticing the overlap is not the same as demonstrating a cause. None of this is an argument for ignoring space weather. It genuinely matters, for reasons that are well established and worth taking seriously on their own terms. If a geomagnetic storm reaches G3 or higher, that is a legitimate concern for airlines flying polar routes for high latitude, electrical grid operators, for satellite operators managing orbital drag and radiation exposure to onboard electronics, and it is a genuine opportunity for anyone hoping to see aurora at latitudes where it doesn't normally reach. Active region 45 firing repeated M-class flares this week, with a non-zero chance of an X-class event in the coming days according to official forecasts, is a real, ongoing story with real consequences. Just consequences that live in the realm of radio communications, satellite operations, and power infrastructure, rather than in the realm of triggering the next eruption at Ambae or anywhere else. It is worth being specific about what those real consequences look like in practice, because they are interesting enough on their own merits, without needing to be inflated into something they are not. During a moderate geomagnetic storm, high-frequency radio communication, still relied upon by some aviation, maritime, and emergency services in remote regions, can fade or drop out entirely on the sunlit side of Earth for anywhere from minutes to hours, which is why space. Weather forecasters issue radio blackout warnings ranked on their own scale from R1, a minor and brief degradation, up to R5, a complete blackout across the entire sunlit hemisphere. GPS and other satellite navigation systems can experience positioning errors that grow from the usual few meters to tens of meters during a strong storm, which matters enormously for precision agriculture, surveying, and aviation approaches that depend on that accuracy, though it is rarely dangerous for ordinary consumer navigation use. Satellites in low Earth orbit experience increased atmospheric drag during a geomagnetic storm because the upper atmosphere itself puffs outward and becomes denser at satellite altitude, which operators have to account for when planning fuel budgets for orbital corrections. And this effect has in the past been significant enough to contribute to the early atmospheric re-entry of clusters of small satellites. None of these effects, however genuinely disruptive to modern infrastructure, involve any pathway that reaches down into the solid Earth or into a magma chamber, which is exactly the distinction worth holding on to when a story tries to connect this week's flares to this week's eruption. It is also useful to place Ambae's current behavior against its own longer history, because that context is far more informative than anything happening on the Sun this particular week. The 2017 to 2018 eruptive episode at Ambae was a genuinely serious event, forcing the temporary relocation of the island's entire population of roughly 11,000 people after heavy ashfall-contaminated water supplies damaged crops and made parts of the island uninhabitable for a period, one of the larger volcanic evacuations in the Pacific in recent decades. That episode unfolded over more than a year in phases, with alert levels rising and falling as monitoring data changed, and it resolved without a single catastrophic climactic explosion, instead settling gradually as the eruptive rate declined. The current unrest, with its intermittent ash plumes reaching a few thousand meters and its ongoing lava effusion reshaping the summit lake, sits well below that 2017 to 2018 episode in scale so far, which is precisely why the alert level has been set at a minor eruption status rather than anything higher, precisely the kind of judgment that comes from comparing today's instrument readings against that volcano's own documented past, not from anything measured 93 million miles away. So the honest way to hold both halves of this story together is this: Ambae, a genuinely active volcano in Vanuatu, continues an eruptive phase that has been documented and monitored for months by the people whose job it is to watch it directly, using ground-based instruments that measure the volcano itself. Separately, the Sun is going through a period of elevated activity from an unusually energetic sunspot region, producing flares strong enough to matter for radio, communications and satellite operations, and to potentially deliver a geomagnetic storm and a wider aurora display in the days ahead. These two things are both real, both worth understanding, and both entirely capable of being true at the same time, without one causing the other. The instinct to connect them into a single unfolding narrative is a natural one, the same instinct that makes any pattern feel more significant once you're primed to look for it. But the actual physical evidence for a causal link between solar activity and volcanic eruptions does not exist in the scientific literature, and claiming otherwise substitutes a satisfying story for the far less tidy, far more accurate picture that Earth's volcanoes answer to the rock beneath them, and the Sun answers to the magnetic dynamo inside itself. Two enormous systems operating on their own separate physics, sharing a solar system, sharing this particular week, and nothing more than that.